Okay, so the terms that are going to be used in this lesson, and you guys can go pull out the exact definition in your books, you can look on the internet, bring these definitions with you to class tomorrow, and listen to how we use them in the notes to help solidify your understanding of what these words mean. So you see the words here, factor theorem, multiple zero, multiplicity, relative maximum, and relative minimum. So we're going to go ahead and look at the first example. And here we're just factoring. So we want to write each polynomial in its factored form. But notice they're of higher degree than 2. But in each of these cases, x is a common factor of all the terms. So I'd factor out the greatest common factor. I'd be left with x squared plus x minus 12. And then you should be able to factor x squared plus x minus 12 the same way you factored in the last unit, giving you x plus 4 times x minus 3. So this would be the complete factored form of that polynomial. For part B, if we factor out x, we have left x squared minus 144. You should recognize this as a difference between squares. So this should factor as x minus 12 and x plus 12, and this would be the factored form of that polynomial. Okay. What we're going to look for next is trying to understand some different things about the graph and finding an equation for each one. These graphs should have arrows at the end. I apologize about that, so go ahead and fix that in your note guide or in your sketches. And we're going to find an equation for each graph. We're not going to find an actual equation. I just want us to look at the zeros and the factors. So notice here that the graph has a 0 at negative 1. This means if you plug in negative 1 into the function as the x value, you would get 0 as the y value. There is a factor theorem that says if that's the case, then x minus that number is a factor. So x minus negative 1 is a factor. And here we see that same thing will occur at 2, so x minus 2 is a factor. But notice it doesn't cross through 2. It comes down, it hits 2, and turns back around. Notice that the behavior here as it touches 2 is very much like a quadratic, where 2 is the vertex of the quadratic. And so that's actually how we represent it in our equation. This is a 0 with a different multiplicity. So negative 1 is a 0 of the function. 2 is a 0 of the function with multiplicity of 2. And I can tell because of the way the graph curves when it hits 2. And that means that the factor shows up twice in the equation. So I would say that one example of an equation for this, just based on the shape and the zeros, is here. Okay? And that's all we're doing. We're not being super accurate because we're not plugging in points to find different a values. We're just shaping it on the shape and the end behavior and the zeros. Okay, so like was mentioned, we are just graphing based on where the zeros are and their multiplicity, as well as if it's positive or negative. So make a note here that a cubic with a lead coefficient that's positive, or something odd degree with a lead coefficient that's positive, goes this way, whereas if that lead coefficient was negative, it would go this other direction. So it's fine for us to keep this positive with our factors. So here we see the same thing again. And we're just going to go through these factors. So we have a factor here of negative 3, a factor of 0, and a factor of 4. Again, how I know those are factors is because the factor theorem says if those are zeros on the graph, then x minus that number must be a factor of that equation. So we have these factors. Again, I'm going to keep lead coefficient positive because the end behaviors are correct for that. And so I'm going to have an x plus 3, and an x minus 4. Notice that none of these factors did I square or cube because they don't have any other multiplicity. They are just going through the zeros as normal. All right, to estimate the relative maximum and relative minimum of the graph. So again, let's assume these graphs go on forever. I'm sorry that the arrows were not there. So then these polynomial functions don't have an absolute maximum or an absolute minimum because they have an end behavior that goes towards infinity and another end behavior that goes towards negative infinity. However, they have relative maximums and relative minimums. These are maximums and minimums that occur in a distinct area of space. So this function here, this is a maximum. This one down here is a minimum relative, a relative maximum and a relative minimum. So in this case, our relative maximum is this point right here, which is the point 0.04. And our relative minimum is this point right here, which is the point 2, 0. So same idea over here with this function, a relative maximum and a relative minimum. And we are estimating if we can't exactly see where they cross. So I will say that our relative maximum up here is approximately at negative 1.5, 4.1, and that the relative minimum is at the point 1.5, negative 4.5. What is the cubic polynomial function in standard form with zeros 1, negative 1, and 4? Again, there would be multiple of these. It's just like the graph that we looked at. There could be lots of graphs that cross through those zeros in that direction. We're going to get a cubic polynomial function. So again, if you know that there's a 0 of 1, then the factor theorem says that x minus 1 must be a factor of this polynomial. Same with x minus negative 1, since it's a 0, and x minus 4. Okay? So this is x minus 1 times x plus 1 times x minus 4. So this is a cubic. They said to write it in standard form, which means we need to multiply it out. So if I multiply x minus 1 and x plus 1 together, I'll get x squared minus 1. Multiply that out on the side if you don't understand how I got that. I now need to multiply that times x minus 4. So I'm going to get x cubed minus 4x squared minus x plus 4. So here it is in standard form. On a note, if I wanted to check my work, if I thought I messed up my multiplication, look back at what you have in the problem. These are zeros, meaning if I plug 1 into this function, I should get 0. If I plug negative 1 into this function, I should get 0. If I plug 4 into this function, I should get 0. So we could easily go back and we could check the zeros of our functions that way. All right, so here is another one. We're going to write a quartic polynomial function with zeros 1, 1, negative 1, and 4. So notice that 1 has a multiplicity of 2. That means the graph at that point would behave like a quadratic. It also means that, yes, x minus 1 is a factor, but it's a factor twice, not just once. Okay, and then x plus 1 because of the 0 of negative 1, and x minus 4. So x minus 1 squared would be x squared minus 2x plus 1. If you don't know how this is happening, go off on the side of your paper and do x minus 1 times x minus 1. We're then going to multiply that times x plus 1 and then times x minus 4. Okay, so I'm just going to go ahead and keep going. So I'll go here. So I'm going to get x cubed plus x squared minus 2x squared minus 2x plus x plus 1. I'm going to go ahead and combine like terms before I start multiplying that with x minus 4. So I have x cubed minus x squared minus x plus 1. That still needs to be multiplied times x minus 4. And then I'll go ahead and do this. So I have x to the 4th minus 4x cubed. Now I'm going to go ahead and distribute the negative x squared. So I'd have negative x cubed plus 4x squared. I'm now going to distribute the negative x. It's going to give me negative x squared plus 4x. I'm now going to distribute the 1, which is going to give me plus x and minus 4. So when I combine like terms, I'm going to have x to the 4th minus 5x cubed plus 3x squared plus 5x minus 4. Again, that's a lot of multiplication, a lot of places that there could be errors. So I would just go ahead and check by plugging in something like 1, and you should get 0. Plug in negative 1, you should get 0. Plug in 4, you should get 0. Okay. All right, the next thing we're going to do is we're going to sketch what these look like on the graphing calculator. And then I want you guys to make notes in the compare and contrast column on the note guide. If you're taking your own notes and you don't have the note guide, then go ahead and what you're supposed to do, write these equations down and sketch the graphs. And then next to them, compare and contrast them. Tell me what's similar. Tell me what's different. Bring this information with you to class tomorrow, ready to discuss with your group. Okay? So let's go ahead and enter these equations into the calculator. So in our calculator, I'm going to go to y equals. I'm going to clear out any equation that's there. I'm going to turn off my plots if I've been graphing data. I'm going to go ahead and type in the first equation, which was x. So as one factor, it had x minus 1 to the second power. And then that was being multiplied by a factor of x minus 3. And that would be multiplied by a factor of x minus 5. So before I even graph some notes, like this would be to degree 4 because I have an x squared times an x times an x. I would end up with something x to the 4th. And notice my factors. X minus 5 should give me a 0 at 5. X minus 3 should give me a 0 at 3. And x minus 1 should give me a 0 at 1. And the fact that it's squared should show me that that 0 has multiplicity of 2, and the graph will behave differently at that 0. So let's go ahead and take a look. I'm going to push zoom choice 6, which is standard, so I can see if it shows up in this window. All right, let me go back and check my equation because I don't think, let's see, x minus 1 squared, x minus 3, did I not square it? Okay, I forgot to square my x minus 1, which is why we didn't see it behave differently at 1. So I'm going to go ahead and just insert my squared. Sorry about that. And then I'm going to go ahead and graph it, and we should see the difference here in behavior. Yeah, see this guy right here? That's how I knew that I didn't graph it correctly, because it should behave like the vertex of a parabola at that 0 because it had multiplicity of 2. Okay, so we see end behavior like a quartic. We see that 0. So go ahead and sketch this next to that equation that we just typed in. We're going to do one more, and then you can go ahead and compare them. So now I'm going to go back to y equals, and this time what I'm going to graph is the factor of x minus 1, this time being raised to the third power. This button right here below the clear button, the little caret button, is the button to insert an exponent. Either it will take you up here like this on mine, and you'll type in 3 and arrow out of it, or it will just make that little caret, and then you'll just put a 3 knowing it's to the third power. And then this is being multiplied times x minus 3 in the second equation. All right, I'm going to look at this graph and see what I have. And notice that as it comes down and goes through 1, it behaves like a cubic graph. It starts to turn and then turns back and goes back down. So a 0 with a multiplicity of 3 behaves slightly differently like what we see here. So make some notes about the behavior that you saw, and some notes about how the graphs are the same and how they're different, and bring those with you to class tomorrow. And then let's go back to our note guide. So you have sketches and notes on these. And let's go ahead and make our own sketches based on our understanding of that. So right here it says sketch the graph of a quadratic. So quadratic means degree 2, so only one turning point. And I'm just sketching, so I'm just going to give myself an x and y axis here. And then it says that has zeros at 3 and negative 3. So I know it has to cross the x-axis at 3 and at negative 3. So I know it goes through the x-axis here, and it's a quadratic. So you could draw this concave up or concave down. You could draw the vertex wherever you want because we don't have that information. This is just an example that meets that criteria. So the next one says sketch the graph of a cubic polynomial function. Okay, so remember, cubic is a function of odd degree. It is of degree 3. And so I expect something maybe like this. Or maybe turn the other way if it had a negative lead coefficient. So positive lead coefficient, negative lead coefficient. All right, so let's see. So sketch the graph of a cubic polynomial. function with zeros at 3, 3, and negative 3. So it's crossing at 3 and at negative 3. But at 3, it has a multiplicity of 2. So if at negative 3, I'm going to go through it like a normal 0. But at positive 3, when I come back down, I'm going to hit it and turn around. Because it listed that 3 twice, which means in its equation it has a factor of x minus 3 being squared, and this multiplicity of 2 tells me that the 0 will not behave normally. Instead, it will turn around like a quadratic at that point. Okay, so the multiplicity of the 0 explains whether the graph goes completely through the x-axis at that point, turns around at that point, or does like the cubic where it kind of curves through that point. Okay, so go ahead and take a minute and fill in F. Explain how the multiplicity of a 0 affects how the graph behaves. If you have to, look back at the calculator sketches that we did, because you had a 0 with multiplicity of 1, 2, and 3 between those two different graphs. Make notes about this and bring this with you to class tomorrow. Okay, so the last thing we're going to do is we're going to find the relative maximum and relative minimum of this graph. Since this isn't graphed for us or something we're going to graph by hand, we're going to go ahead and do it on our calculator and see what we get. So on my calculator, I'm going to go to my y equals, clear out whatever's in there, and type in this equation. So x cubed, so x to the third, minus 4x squared, minus x, plus 4. I'm going to go ahead and see if I can see what I want to of this graph. So when I look, okay, so this is shaped like a function that has odd degree, which is good because mine was a cubic, so this seems like a good cubic shape. And so it has no absolute maximum or minimum, but it does have a relative minimum right here and a relative maximum right here. So to find this, or excuse me, the other way around, relative maximum here and a relative minimum here. So we're going to do the same things we did to find maximums and minimums of quadratics. I'm going to go to second calculate, and I'm going to choose choice 4, which is maximum. Right here is the maximum I want to calculate. So I need a left bound. I press enter. It asks for a right bound, so I go to the right and press enter. It says guess, and I press enter again. And it gives me my maximum. So you can record this as the maximum for that function. So you would just want to write down that the maximum is at negative 0.12, comma 4.06. I'm going to do second calculate again, and this time I'm going to choose minimum, and I'm going to scroll over here to calculate this relative minimum. So again, it's asking me for a left bound, so I'm going to go to something that is to the left of the minimum I'm trying to calculate and press enter. Right bound means to the right, and I will press enter. And I want it to guess, so I press enter again. And I will get the point 2.798.21. So those are my, negative 8.21. Those are my relative maximum and relative minimum for that graph. And so record those here on your note guide. Make sure you wrote answers to the previous questions because we will be discussing those in class, and they will help you with working on homework 1 and homework 2.